This lesson is on 6.5, Properties of Logarithms. We start off by some basic properties of common and natural logarithms. Now these things that we're going to write in this box right here are things that you should already be somewhat familiar with. Let's start off right over here. This first one is saying log base a of 1. This is looking for the exponent that you put on a base of a to get 1. In other words, a to the what power gives you 1, and the answer is 0. So with common logarithms, that's when it's base 10. And when it's base 10, it's the same as not writing a base at all. And so once again, 10 to the what power will give you 1, and the answer is 0. For natural logarithm, that's when you have a log base e. And the shorthand for that is ln. So ln 1, or the natural log of 1, is asking for e to the what power gives you 1. And the answer once again is 0. So you should know that log base a of 1 is 0. Log base 10 of 1 is 0. And log base e of 1 is also 0. Next, we have log base a of a. The question is asking, a to the what power gives you a? Well, the answer is 1. A to the first power is 1. So the common log problem is 10 to the what power is 10. And the answer here is 1. For natural log, it's log base e of e. So e to the what power is e. And the answer is 1. So for this second property, make sure you know that log base a of a is 1, log base 10 of 10 is 1, and log base e of e is 1. So as long as this base and this argument are exactly the same, the logarithm will equal 1. Next, we have log base a of a to the x. The question here is, a to the what power will give you a to the x? And the answer is x. You raise a to the x power to get a to the x. For common logs, it will be log base 10 of 10 to the x is the same as log of 10 to the x, which is x. Then we have log base e of e to the x, or ln e to the x, and that equals to x. So notice that all three of these are equal to x. Okay, the last property that you should know is when we have a raised to the log base a of x. Now this one's a little bit harder to think about, but remember, this logarithm represents the exponent you put on a to get x. And so if this is actually the exponent that we're putting on a, then this should equal to x. Because if log base a of x is the exponent you put on a to get x, then a to that exponent should give you x. This one might take a little bit of time for you to process in your head. Okay? So the common log version of this would be 10 to the log base 10 of x, which is the same as saying 10 raised to the log x is equal to x. And here, e to the ln x will be x. These last two properties also follows from the fact that logs and exponentials are inverses of each other. But we won't get into that for now. All right, so this brings us to writing these 4 properties. And by 4 properties, I mean these 4 with base 2. So first would be log base 2 of 1, which is 0. Log base 2 of 2, which is 1. Log base 2 of 2 to the x is x. And then 2 raised to the log base 2 of x is x. With a base of 1/3, it will be log base 1/3 of 1 equals 0. Log base 1/3 of 1/3 is 1. Log base 1/3 of 1/3 to the x is x. And 1/3 raised to the log base 1/3 of x is x. Now, we're going to skip example 2 for now. Example 2 proves the properties that we are about to write on the next page. We will leave example 2 to the next class period. So now, let's just go on to the next page. Right before the break, you learn these 3 properties of logarithms. The product property says this: log base a of m plus log base a of n equals to log base a of m times n. So when you have 2 logarithms with the same base added to each other, it equals to 1 single log with that base of the arguments multiplied by each other. So m is the argument here, n is the argument here. So this argument is m times n. You saw this before spring break, but we will also prove it later this week. The quotient property says log base a of m minus log base a of n equals to log base a of m divided by n. So here, when we subtract 2 logs with the same base, it can be rewritten as 1 single log with that base with the arguments divided by each other. So m divided by n. Again, we will prove this later this week. The power property says log base a of m to the r power is equal to r times log base a of m. So notice that the exponent on the argument can be moved to the front in this property. So let's look at some examples to see these 3 properties at play. Example 3a. To expand the following logarithms, notice that this is 8 times x. And so 8 times x is sort of like over here where you have m times n. So that allows us to write it as 2 separate logs with a plus in the middle. So this will be log base 2 of 8 plus log base 2 of x. Notice that we have argument of 8 and x and a plus in the middle. Now this can be simplified further because log base 2 of 8 is 3. So this is 3 plus log base 2 of x. Okay, let's look at part B. Part B, what we see in part B is p divided by 81. And over here, up here at the top, we have m divided by n. And what that allowed us to do is write it as 2 separate logs with a minus in the middle. And so this is going to be log base 3 of p minus log base 3 of 81. Notice again that we have a minus right here, and you have p and 81. Now this can be simplified further because log base 3 of 81 is 4. So this is the final answer. Okay, let's look at part C. Part C is going to incorporate the product property as well as the power property. So let's take a look. First of all, we have 64 times x to the 8th. So since it's times, it's going to correspond to a plus sign. And so what we have is log base 4 of 64 plus log base 4 of x to the 8th. Now log base 4 of 64 is just 3, because 3 is the exponent you put on 4 to make 64. But this right here, notice that we have an exponent on the argument. And the power property allows you to move that exponent on the argument to the front. So you have 8 times log base 4 of x. And so this is the expanded version of this logarithm. All right, now let's look at example 4. Example 4 says, describe log base 2 of 8x as a transformation on log base 2 of x. So the first thing we're going to do is expand this into 2 separate logs. Notice that 8 is being multiplied to x. So that's why it leads to this plus sign right there. And so then this is 3 plus log base 2 of x. And this 3 means up 3. So guess what? What I just did is supposed to be down here in part B. So I'm going to now erase over here, because if it's up 3, that's a translation. So we have translation over here, okay? All right, so how do we write it as a stretch or shrink? Well, that one doesn't require us to rewrite it at all, because 8x is a horizontal shrink by a factor of 1/8. That's a concept from Algebra 2a. When you have 8 timesing the x, that's a horizontal shrink by a factor of 1/8. So this is an interesting finding. If we have this as the parent graph, so if we think of this graph right here as the parent graph, then a horizontal shrink by a factor of 1/8 gives you the same graph as moving this parent graph up 3. That's really weird. We can look at this by graphing it on the calculator and seeing why that is. Or we can graph it by hand and see why that is. We won't do that right now, but just know that these are equivalent. Interesting. All right, let's go to the next page. All right, this page involves a bunch of pretty high-level problems. And so I will walk you through these carefully. First of all, we have an argument here that is being cube root or cube rooted. So that's the same as log base 5 of, I can think of it as raising this whole thing to the 1/3 power. Because cube rooting something is the same as raising it to the 1/3 power. Then the power property allows us to move this exponent to the front. So the first step becomes 1/3 times log base 5 of x cubed times y squared over k to the 9th times z. Okay. Now we have 1/3 times this whole thing, which we're about to expand. Now x cubed is being multiplied by y squared. And so when it's multiplied, recall that you can add or expand them into multiple logs and add these arguments, or add these logs. Let me say that again. Because this x cubed is being multiplied to y squared, we can write them as two separate logs with a plus in the middle. Okay? Now k to the 9th and z are both in the denominator. And when it's in the denominator, we can minus log base 5 of k to the 9th minus log base 5 of z. Notice that both of these have a minus in the front because both of these terms or factors are in the denominator. All right, now lastly, we are going to move this to the front, move this to the front, move this to the front, and there's nothing to move for that last one. So then our answer, our next step is 1/3 times 3 times log base 5 of x plus 2 times log base 5 of y minus 9 times log base 5 of k minus log base 5 of z. Then we can distribute this 1/3 into all four terms. So our final answer is going to be 1 times log base 5 of x plus 2/3 times log base 5 of y minus 3 times log base 5 of k minus 1/3 log base 5 of z. And that's our answer. Okay. Try the next one on your own first. And so if we can pause this video for a few minutes for everyone to try part B first, and then play the video afterwards. All right, let's look at part B now. So the square root is the same as raising everything to the 1/2 power. So the first step is to rewrite this argument as x cubed times z over y squared to the 1/2 power. Next, we're going to move this 1/2 to the front, giving us 1/2 times log base 3 of x cubed times z over y squared. Then we're going to expand this log into 3 separate logs. The first log is log base 3 of x cubed. The second log is log base 3 of z. And the third log is log base 3 of y squared. Now notice that we have a plus sign here because x cubed and z are being multiplied. Notice we have a minus sign here because y squared appears in the denominator. So anything that any part of the argument that is in the denominator would have a minus in front of that log. All right, now next we're going to move this 3 to the front and move this 2 to the front using the power property. So we have 3 times log base 3 of x plus log base 3 of z minus 2 times log base 3 of y. And then we're going to now distribute this 1/2 to all 3 terms, giving us 3/2 log base 3 of x plus 1/2 log base 3 of z minus 1 log base 3 of y. All right, now we're going to do the reverse by condensing multiple logs into one single log. So the first thing we're going to do, and we have to do all these things in reverse now, we have to first move this 7 up to the exponent of the argument. We have to move this 1/2 to be the exponent on the z, and we have to move this 8 to be the exponent on the n to the 5th. So the very first step will be log base 2 of x to the 7th plus log base 2 of z to the 1/2 minus log base 2 of n to the 5th to the 8th. Then we have log base 2 of x to the 7th plus log base 2 of z to the 1/2 minus log base 2 of n to the 40th power, because n to the 5th to the 8th is n to the 40th power. All right, so now we have 3 separate logs, but they all have the same base, which means that we can write them all as one single log with that base. Notice that there is a hidden plus sign in front of this first term, telling us that x to the 7th goes in the numerator. Then we have a plus sign, so that tells you that z to the 1/2 also goes in the numerator. But we have a minus sign here, which tells us that n to the 40th goes in the denominator. And this is our answer. All right, this ends this video. Now you may begin tonight's homework, which is homework 6.5a.